All right. So today we have Pieter Bomans who will unravel the holomorphic twist for us. Take it away.
Thank you very much, Julius. Thank you for having me here in this beautiful seminar series. And thank you everyone for being here. So as Julius already said, today I will be talking about the holomorphic twist and try to unravel this twist. This is based on work in progress with Nick Garner in Oxford, Brian Williams from Boston, and Jing Shang, who also was in Oxford. And it's based on two papers that came out last year or a few months ago, a paper of 2 years ago, and some work in progress that I will comment on along the way. Good. So let's start with some motivation. Well, the main motivation is QFT is hard, so we want to make it easier. If we think about a QFT, correlation functions of local operators are among the most fundamental observables. In principle, if we're all powerful, we can compute them. Well, this picture summarizes the thing we have to do in principle. So if we have an OPE, which we can think of as operators at separated points, if we bring them close together, we can expand them in this term in terms of the other operators. So if we have an operator algebra, this equation in principle tells you how to compute any correlation function. So this equation is strongly constrained by associativity, but in general, it's still incredibly hard to compute this, to access the OPE data. And if we don't have conformal symmetry, in general, this OPE is not even convergent. So we really are, we really struggle to make progress. So in order to make some progress, we need more structure. And this structure will come from symmetry. So I forgot to mention in the beginning, but if something is not clear or if you have a question, please do interrupt me at any time. Good, back to structure. So if we have no symmetry, if we just have a generic QFT, life is very hard and we don't know how to compute anything. So how can we get this extra structure? And I will argue for two ways of adding structure. One is conformal symmetry, and the other is supersymmetry. So example one, in a 2D CFT, we have conformal symmetry, and this conformal symmetry is actually enhanced to an infinite dimensional symmetry algebra, the Virasoro symmetry algebra. And in some cases, together with associativity, this infinite dimensional symmetry algebra allows us to completely solve the theory. So this is, from this famous work where the minimal models were introduced. So in these cases, we really have this infinite dimensional symmetry that allows us to completely bootstrap the theory and solve any correlation function we want in principle. So that's clearly a very nice thing to have. Another thing that we have learned how to deal with is if we have a supersymmetric theory. So in that case, we can apply supersymmetric localization. So if we have a theory that contains some superchurch Q, in many cases, Q-closed observables localize to some simpler matrix model often. And using this matrix model, which is much simpler than a full 4D QFT, we can in principle, again, compute everything exactly. So we have to still solve some complicated matrix integrals, but these are doable things. And in certain regimes, we can definitely get a lot of insight from this point of view. However, with this supersymmetric localization, when we compute something, these Q-closed examples, these Q-closed observables, in the most well-known examples, give access to free energies, Wilson loop expectation values, maybe surface operators, but typically not local operators. So the thing that we wanted to compute, correlation functions of local operators, are typically very hard to get through localization. The best you can do in many cases is to get integrated correlators by taking a partition function with some parameters and taking in derivatives, but this is not capturing like the spatial structure of these correlators, so it's not everything we were hoping to get. So we will go one step further in this talk and try to get more access to kind of local operators. And we look for situations, we do so by looking for situations where the two situations I described above, where we have this infinite dimensional symmetry algebras, and we localize to simpler theory, where these two things combine. So this arises often when we choose some supercharge and we localize the theory. But in the previous examples I discussed, the theory localized to a zero-dimensional matrix model. Sometimes it can also localize to one or two-dimensional QFT that is still much simpler than the original QFT. So famous examples of this type of idea are the 4D n equal 2 SCFTs that were that were studied in this work and were shown to contain a sector that is isomorphic to a two-dimensional VOA, so a chiral 2D CFT. So we're back to this infinite dimensional symmetry story where we can compute things exactly. So using this kind of correspondence between 4D n equal 2 SCFTs and VOAs, we can now learn a lot about local operators in some that live in some plane. The same thing happens in 3D n equal 4. So if you have a 3D n equal 4 theory, there is a sector that is isomorphic to a one-dimensional topological quantum mechanics. So these kind of theories, there's some subsector of the theory that is isomorphic to a much simpler theory, which still has some, it is still a QFT in more than zero spatial dimensions. So you can get access to real dynamic and kinematic data of these correlation functions, and not just the integrated ones or extended operators. So this is for 4D n equal 2, 3D n equal 4. In this talk, so these things have been studied for a while. In this talk, I'll introduce a kind of more, the next step in this kind of program, where we'll now talk about 4D n equal 1 SCFTs. And we'll study the resulting theory after we twist with some nilpotent supercharge. Good. So this was kind of the motivation. The rest of the talk, I will introduce the holomorphic twist. So what happens when we twist 4D n equal 1 SCFTs or SQFTs? Once I've introduced the framework of this holomorphic twist, I'll continue to discuss how symmetries and anomalies can be described in this kind of twisted language. I'll continue with some words on what happens if you have extended supersymmetry. So if you don't just have n equal 1, more supersymmetry, there's extra structure that appears in this holomorphic twist. And I'll finish with a summary and some more things to do. Good. Let's get started with the holomorphic twist. Any questions so far? Good, good. So the holomorphic twist. So far, I've said twisting many times. So what do I mean with twisting? If we have supersymmetric theory, then there is some supercharge in the supersymmetry algebra. So first step of twisting is picking one specific supercharge we like. Let's call it bold Q here, and we'll add this Q to the BV or BRST differential. And instead of what we usually do if we look at gauge theory is we look at all the operators and we look at the cohomology of the BRST differential, which projects us to all the gauge invariant states. Here we'll do exactly the same. but we change this differential from the usual BRST differential to this bold B, which is d BRST plus Q. And this is now the BRST differential of the twisted theory. So in this, well, if we want to look at the observables of this twisted theory, this is just the same as we would do in usual BRST. Instead of looking at the cohomology of the BRST differential, we now look at the cohomology with respect to this bold B, and that gives us the space of observables in the twisted theory. And the final step of the twisting procedure is choosing a homomorphism. So we pick, we have our original Lorentz group spin D. We have the R symmetry group GR, and this group G, which is the reduced Lorentz group, or the new Lorentz group, which we pick a homomorphism. So this G is the Lorentz group after twisting, and it's chosen in such a way that Q, the supercharge we picked, is a scalar under G. Good, so let's see what this kind of thing does when we look at for the n=1 SCFTs, or SQFTs even. So if we have a 4D n=1 SQFT, the supersymmetry algebra contains the following generators that we all know and love. We have some translations, rotations. We have our favorite supersymmetry supercharges, and if we're lucky, we also have some R symmetry. The commutation relations of the supersymmetry algebra. So we have our speed and our supercharges, Q and Q tilde in 4D, and they have the following commutation relations. Q tilde anti-commutes to a translation, and the other anti-commutators vanish. So if we now pick a supercharge bold Q, so for convenience we'll pick Q minus, but this is just an arbitrary choice. This choice selects a specific complex structure on R4, so that we can treat it as C2 with complex coordinates Z and Z alpha and Z alpha bar. So we have a 4-dimensional theory, or C2. So we have two complex coordinates, Z1 and Z2, and Z1 bar and Z2 bar. So an important observation now is that when we look at the commutator of this Q bar, this bold Q on Q tildes, we get exactly the anti-holomorphic translations. So what this means is that anti-holomorphic translations are Q exact. So once we go to cohomology, this means that if we translate operators in an anti-holomorphic way, this becomes this doesn't change the cohomology. This is just irrelevant. So everything that happens in this twisted theory will be only holomorphic. All the anti-holomorphic dependence is exact, so we don't care about it. So repeating what I said is, once we now pass to the cohomology of the supercharge, we therefore get a theory that is holomorphic in a cohomological sense. So all the anti-holomorphic dependence is just trivial in the twisted theory. Once we do the twist, we identify part of the R symmetry with part of the Lorentz group. This breaks our Lorentz group, and the thing that we are left with is SU2, which is generated by the dotted part of these rotation generators. In the case that our n=1 theory had some unbroken U and R symmetry, we have one additional generator, which is this mR, by combining m plus minus with the R symmetry generator. And this extends SU2 to U2. So then we have the full the remaining like Lorentz group is exactly the holomorphic rotations of these V alphas. So finally, the space of operators that survives this twist is just the Q cohomology of local operators. So all the operators that are annihilated by Q, but are not Q exact. So since the operators are, in this case, annihilated by one supercharge, we call them semi-chiral. So this is just an analogy with the usual chiral operators that are annihilated by two chiral supercharges. So the operators that we'll care about are semi-chiral operators. So the operators in a supersymmetric theory, they're not just separate operators, but because of supersymmetry, they organize nicely into multiplets. In a generic, if we have a generic multiplet, so long multiplet, there's no null states. So operators are Q-closed only if they are Q-exact. So this means that a long multiplet does not give rise to any non-trivial Q cohomology class. So they don't contribute to the holomorphic twist. However, when a BPS bound is saturated, these multiplets become short. There's some null state that appears. And in fact, we see that any short multiplet contributes one operator to the Q cohomology. So this is a statement that I want to emphasize. When we discussed briefly these 4D n = 2 cases, where you go from a 4D n = 2 theory to a VOA, the VOA captures the Schur sector of the theory. So this is a subclass of all the BPS operators. So the index, in a sense, captures all BPS operators, the superconformal index, and the Schur sector only captures like part of it. So what we see here is that the holomorphic twist captures all operators that contribute to the superconformal index. So this is really a powerful statement that everything that contributes to the index is seen by this holomorphic twist. So this is, in a sense, the maximal protected sector that you can imagine. So now we can look at the OPE between two semi-chiral operators. And then we see the following, that if you have the OPE between two semi-chiral operators, it's necessarily regular. So you get another semi-chiral operator, and the rest is Q exact. And this is simply due to Hartog's theorem in complex analysis on C2, which says that if you have a function on C2 that is singular just at one point, you can always extend it to a fully regular theory. And hence, like points like singularities.
Oh, sure.
Is there a question? Oh, good. So because of this theorem in complex analysis, we necessarily see that the OPE is always regular and there's no singular terms allowed in this OPE. So in other words, the operators form a semi-chiral ring. So this is kind of disappointing. Usually when we look at OPEs, all the interesting parts are captured by the singular terms in this OPE. But we kind of see that if we naively treat these operators, we only get regular OPEs. So we
could I ask a question about that? So
yes,
there's not a symmetry necessarily that protects these dimensions so that there's not this singularity. It's just this Hartog's theorem.
Yeah. So there's no, not really a symmetry statement that's, well, I can't think of a symmetry statement that prohibits singular terms in the OPE. The simplest way, yeah, it's like it's just
okay.
By complex analysis. And you can think of this like as, since everything is independent of the anti-holomorphic directions. If you want to bring two operators together, you can always separate them in the anti-holomorphic direction kind. So it's easier to think about this in a holomorphic topological theory, where you can never get holomorphic. You can never get singularities because you can always move in the topological direction and avoid the singularity. So it's a bit harder to think of in this purely holomorphic setting, but it's the same statement in a sense that it's just not allowed by.
But I'm just wondering whether this result sort of kind of means that you get something like analogous to a U1R symmetry, or some sort of U1 symmetry gets enforced on this twisted sector.
So maybe there's an interpretation that is, yeah, there is. So there is a kind of holomorphic dilation operator that is exactly this. What is it here? This m-ary, and that has imposes the same kind of grading as the usual dilation, which might impose something like this, but you don't necessarily have this additional R symmetry. Like in n=1 theory, you can have an anomalous U1R, and then this m-ary is just not there. So this grading does not have to be there, this R grading. So this statement is somewhat stronger than just imposing some R symmetry. It also holds when you don't have a U1R symmetry.
Okay, thanks.
Good. So so far we're a bit disappointed because we don't get anything. We don't seem to get too much interesting stuff. But luckily we can do more. So in order to find some more interesting structure, we can remember that these theories come from a bigger theory, and we can keep track of the descendants of the semichiral operators. So it's useful to introduce these reduced superfields, which look as follows, where we have O0, which is our original semichiral superfield, and we act on it by this operator, which we can do. So this is like a superfield, and because we did this twist, the superspace coordinate theta now acts like an anti-holomorphic one form. So we get this 0 form part, a 1 form part, and a 2 form part, where this is the first descendant and the second descendant of Q. So we similarly have some supercovariant derivative that we can introduce, just the usual things in a similar way that people do this in standard n=1 superspace. And we get some sort of holomorphic descent relations. So the statement that the zeroth component is a semichiral field now becomes this statement that the full superfield satisfies this equation. So the Q cohomology of the operators is isomorphic to the space of semichiral superfields. And these superfields are useful because they don't only capture our semichiral superfield, but also their descendants, which are not necessarily Q-closed, as you can see from this equation, and that will be important. So as we saw, Hartog's theorem tells us that OPEs between semichiral operators are regular, but there can be singularities in the OPEs of operators that are not Q-closed, such as these descendants that appear in semichiral superfields. So using this fact, we can build a collection of secondary operators that allows us to extract all these singularities from OPE data of operators with descendants of a second operator. So how do we see this? we can extract these data by looking at integrals of the following form, where we mimic what we did in 2D, what we do in 2D CFT. We have two operators, O1 and O2, and we add some rho, which is anti-holomorphic form on C2 without the origin. And if we want to compute this, the product only depends on this class rho, which is a cohomology class. Good. So we can define some basis of operators where a difference with in one complex dimension is that now we have higher cohomology, and that will be, in a sense, the origin of all the weirdness and the extra structure that we see. So we find in the zeroth cohomology, we find these usual powers of z, where m and n are bigger than 0, and they're very similar to what in a 2D CFT looks like positive modes. While in the 0-1 cohomology, we get these derivatives of the Bochner-Martinelli kernel, where the Bochner-Martinelli kernel is the Green's function for the Dolbeault operator. So with these explicit representatives of the cohomology classes at hand, we can introduce an infinite amount of products labeled by O1, O2 with subscript m and n by inserting one of these representatives. And this is exactly what you do in 2D, where you act with the modes of an operator on an operator on a different operator. So what this does is, the positive modes, they capture precisely the singular part of the OPE, while the negative modes capture these regularized kind of products. So we see that even though the OPE of two semi-chiral superfields is regular, and we don't seem to get so much new information, we can build this whole set of products where you can extract a bunch of a lot more OPE coefficients between the operator and the descendants of the second one. So this allows us to access a much wider class of OPE data. So this is not everything. We can go crazier. We can think of, we can rewrite these binary products as integrals over configuration space of 2 points. So this is just a simple rewriting using just converting a boundary integral to a bulk integral. So we can rewrite this as a configuration space of 2 points, where this configuration space of 2 points is just C2. It's if you put 1 point at the origin, the other point can be anywhere else. So this definition allows us now to generalize to any number of insertions. So we can put n operators in there and write down an integral of the following form, where we now integrate over some chain in the configuration space of n points and some cohomology class in the configuration space of n points. And this gives us a bunch of n-ary operators, which all encode some of the OPE data of these twisted theories. So at the moment, we have good control over this binary bracket, but we don't really have a satisfactory non-perturbative definition of these n-ary multi-OPEs that appear in this bracket. But nonetheless, we can compute things perturbatively. So we can still treat this multi-bracket as some as just an OPE in a free theory, and then expand and do the rest.
What's the problem with just defining them as successive sort of OPEs?
Good. Yeah, I should have emphasize this. So in standard non-holomorphic, so full CFT, this is indeed what you can do. It's exactly the thing that one can do is any limit where you successively take where you take 3 points together, you can always treat it as taking 2 points together and then smashing a third point together. And there's no new information in the limit where 3 points go together in the same way. In the holomorphic twist, there's a bit more flexibility because there we have well, as we will discuss in a bit, the symmetry algebra now becomes a L-infinity algebra. So everything is endowed with some L-infinity structure, which in a sense means that associativity is not exactly preserved, but it's preserved up to some higher brackets. So these higher brackets, in a sense, capture the non-associativity of the holomorphic OPE. So unlike a real QFT, these kind of brackets do encode something new, and this like multi-OPE where 3 points come together can in some cases contain some really new information. So this is in a sense the reason why they're not trivial, and it's
So
not really
you're going to show us this non-associativity below. So
the non-associativity itself, I will not talk about much, but I will introduce this L-infinity structure and how the Jacobi identities that are usually encoding associativity are changed.
Okay, thanks.
Yes. So all this structure of binary and n-ary secondary brackets together with the OPE and gives this holomorphic QFT the structure of a higher analog of a vertex operator algebra as defined by mathematicians. So this is just a 4-dimensional generalization of the usual 2-dimensional chiral QFT. Good. A final piece of machinery that we will introduce are lambda brackets. So we introduced this infinity of products here, but it's often useful to collect all this infinity of products in a generating function, which we denote as follows. This is the lambda bracket, which we have this exponential here, which if you expand it, it gives you all the positive modes in a sense. So this lambda bracket captures all the positive modes, all the positive products. So this gives us access to it's getting hot here. This lambda bracket gives us access to all the singular terms in the OPE. And it's often, it's this lambda bracket that is easiest to compute, or at least the most convenient thing to compute. And similarly, for all these higher brackets, we can compute, we can introduce a generating function which captures all the positive higher products. So these kind of things are again we again run into the same problems that we don't really have a good non-perturbative definition of what these brackets actually mean. But in perturbation theory, as was defined in work by Gaiotto, Budzik, Kulp, Williams, and Wu and Yu, and follow-ups, they showed that, they introduced an efficient perturbative definition of these things, which we will use throughout this work. So for the people that are well, into 2D VOAs and their relatives, what we get if we take the holomorphic QFT, all the operators equipped with these kind of lambda brackets that has the structure of a homotopic Lie conformal algebra, which is again this 4-dimensional generalization of a usual Lie conformal algebra. So this structure is somewhat, well, weaker than a full higher VOA. It doesn't have the regular parts of the OPEs, but it's easier to compute with. And in a sense, it contains all the same information that we care about. Good. So to get some intuition into how all these twisted theories look like, we can consider some Lagrangian SQFT. So if we have a Lagrangian theory with vector multiplets and hypermultiplets, the twisted theory has a very simple presentation. So for every vector multiplet, we get a BC system, and every chiral multiplet gives us a beta gamma system. So if we have some gauge theory with matter in a certain representation, then we get the following very simple twisted Lagrangian. For B and C, we get this very simple BC BF-like Lagrangian, and the W here is just exactly the n=1 superpotential. So for n=1 Lagrangian theories, there's a very simple map between the usual Lagrangian theory and the twisted Lagrangian theory. But well, we already see that we have first order action, so it's a lot simpler to compute. And again, well, if you have such a theory, the lambda brackets are very simple. Beta gamma have this kind of lambda bracket BC. So this is kind of trivial, but if you build composite operators, you can find the stress tensor, and you get more things that depend on lambda, and that's where the singular OPE terms and the singular dependence is hidden. Good. So that was a lot of formalism. So now let's put this formalism to use and study these holomorphic field theories that we obtain from n=1 theories in some more detail. And in particular, we'll look at their symmetries and anomalies. So when a physical theory enjoys a global symmetry, then it contains some sort of conserved, well, it contains a conserved current, the continuous global symmetry. And if you look at if you look at the conformal multiplets, this conserved currents always sit inside some short multiplet. So we get a semi-chiral superfield J, ball J, where the current in which the current sits. So every conserved current gives rise to a semi-chiral superfield, but because we have a holomorphic theory, we can now multiply this current with any del bar closed form, and we get another semi-chiral superfield. So the conservation equation in the holomorphic theory is just del bar J = 0. So we see that for any such multiplying this conserved current with any anti-holomorphic thing, or del bar closed, so holomorphic, any del bar closed form, we get a new semi-chiral superfield. So just like in 2D CFT, we get an infinite dimensional symmetry algebra. So this is really a powerful statement, because as in 2D CFT, we now get much more constraints on everything that appears. And there's, well, maybe in the future, hope of if we take if we take some simple models that we can actually solve some holomorphic field theory in the same sense as we could solve minimal models in 2D. So a weird thing that happens, or some more exotic thing that happens in 4D, is that unlike in 2D, symmetry algebra is no longer of Lie type, but there's some homotopic nature, which means that they're naturally described in terms of L-infinity algebra. So I'm not really saying a lot here about L-infinity, but this is exactly what I was saying before, that you don't have just Jacobi identity, which tells you that this repeated commutator is 0, but it's 0 up to some 3 bracket. And these exactly reflect these higher brackets that we saw in the first part. So as I already said, as a first example of such symmetry, let's look at space-time symmetry. So as I already said, the twist breaks the full spin 4 Lorentz group to SU2 or U2 in case we have a preserved U1R. And I'll focus on the U2 case so that we have all kind of all holomorphic rotations. So we can model this kind of symmetry algebra that we get as the infinite dimension extension of this U2 reduced Lorentz group is now the width algebra. The width algebra is exactly the vector fields on C2 without 0, and they satisfy the standard Lie bracket between vector fields. So if we have some holomorphic vector field V, it acts on local operators as follows. So we have V, where we exactly take this mode expansion where Vi are, well, these components, and Si, S is the superfield that comes from the stress tensor. So just like the thing we get in 2D, if you act with these vector fields or elements of the width algebra, you generate, well, you act with modes of the stress tensor, so you generate the space-time symmetry algebra. So this is the classical story, but as we know from 2D, this kind of Lie algebra, well, in 2D, the width algebra has a famous central extension, which gives rise to the conformal anomaly or the central charge in the Virasoro symmetry algebra. In 4D, we can do the same. So in this width 2, we can find a Virasoro 2. But unlike the 2D case, now the central extension does not appear as a Lie type central extension. So it doesn't appear in this 2 bracket. It appears in some higher brackets. So the central extension makes this Lie algebra into an L-infinity algebra. So we get some non-trivial 3 brackets between 3 vector fields. That is, well, so this, and the space of 3 co-cycles is exactly 2-dimensional. So what this means is that we get, in this case now, not just 1 central extension like in 2D, but we get 2 central extensions. And these 2 central extensions exactly correspond to A and C. So I'll say more about this in a second when I phrase it in terms of lambda brackets. But first, let's look at the flavor symmetry. So if we have flavor symmetry, I already said there's a current that we get, a current superfield. We can multiply this current by any holomorphic superfield, any holomorphic, any del-bar closed operator, and the full infinite dimensional symmetry algebra is something like a Kac-Moody algebra. So this is again a generalization of what we know from 2D, where we get a Lie algebra valued holomorphic, anti-holomorphic form. And there's again a central extension that appears at in a tree bracket. So here the expressions are a bit simpler, so it's easier to look at. So we can see if we have the two brackets between two modes of this current. So as we introduced before, when we multiply these things with this del bar operator, it's kind of like the modes of a 2D CFT. And there's this simple algebra that is exactly like well, the Kac-Moody algebra. If we play with if we have the Kac-Moody algebra and we add a central extension, then usually you would get something like plus k times, well, k times some number. But in this case, this doesn't happen. In this case, we get this central extension in a tree bracket. So there's some higher operation that is proportional to this k, which is exactly the 't Hooft anomaly related to this symmetry. Good, so we've seen that these symmetry algebras, so in the holomorphic twist, that the symmetry algebras are enhanced to some infinite dimensional symmetry algebras, which are the 4D generalizations of the Virasoro symmetry algebra and the Kac-Moody algebra. So again, it's, well, we just introduced them in terms of the modes, but it will often be useful to write it in terms of these lambda brackets, where we can collect all positive modes in one equation. So for the stress tensor, we get this kind of two bracket, where we get some, well, something that looks very similar to what you would get for in 2D. While in 3D, we get this kind of more complicated, well, for the tree lambda bracket, we get this more complicated structure, where we see that there's one term with A minus C, and some tensor structure, which depends on lambda, and a second term with 3C minus 2A, and a second tensor structure. So the names are just chosen because if A equals C, then this part is left over. And for a free vector, we have, well, this thing vanishes so that you get this. So there's nothing special about these names. They're just a choice of two independent tensor structures. But the important thing is that this exactly, well, captures the two-dimensional central extensions, which give us the conformal anomalies of a four-dimensional theory. Similarly, for the flavor symmetry, as we saw in the previous slide, there's a two bracket that looks very much like what you would expect, but then there's this additional three bracket where the 't Hooft anomalies or the central extension is hidden, and the DABC is just the symmetric invariant of the algebra G. So summarizing, if we have this kind of, if we have some global symmetry in the holomorphic twist, in the twisted theory, the symmetry is enhanced to some infinite dimensional symmetry algebra, very similar to Virasoro or Kac-Moody, where the central extensions are exactly the conformal anomalies and the 't Hooft anomalies of the physical theory. And there's, well, this can be easily extended to mixed correlate. Well, we can also compute mixed correlators between stress tensors and currents, and that this gives us flavor levels and mixed 't Hooft anomalies that are all encoded in this kind of mixed ternary lambda brackets. Good. So that was the symmetry structure. And before we move into anomalies, any questions? Good. Let's continue then. So if we want to describe anomalies, what we usually do is couple the field to some background, couple the theory to some background gauge fields for the flavor symmetries. So how do we do this in these holomorphic theories? So we have our stress tensor superfield. Usually it couples to the metric, but in this case, the background field is just Beltrami differential, which captures the complex structure deformations, not the full metric deformations. And similarly for the current, we don't couple to a full background connection, but only a holomorphic background connection. So this parameterizes now deformations of a holomorphic flavor symmetry bundle. And these backgrounds have to satisfy these Maurer-Kaftan equations, and this is just to impose gauge invariance. So the minimal coupling takes a very familiar form, where we have the original action, where we add this linear coupling, where now the only difference is that A is a holomorphic connection and U only parameterizes the complex structure deformations. So the anomalies of holomorphic QFT show up in various ways. In one sense, they show up as a failure to solve some equivariant master equation, which is maybe the most abstract and well, only for people who really care about BV. The BV formalism, this equation tells you that if you introduce these background gauge fields, something goes wrong with, well, you can't solve this master equation, which tells you that the theory is invariant under the symmetry. A more familiar way to see this is that if there's an anomaly, this is encoded exactly in the fact that the current is no longer conserved. So this current JF, if we have an anomaly parameterized by K, there's exactly this usual term that appears. And this tells us that if there is an anomaly, the current is no longer a semi-chiral superfield, but it's get lifted from cohomology. Once we turn on this background field, so in case this is a background field, when we don't have backgrounds, we're still happy, and this is the usual Toft anomaly. When these are dynamical fields, the symmetry is really broken. It's an ABJ anomaly, and the superfield is really lifted from the cohomology. A last way, which I will not discuss here, is that you can also introduce really a holomorphic version of descent formalism, where you have a holomorphic anomaly polynomial, and you can see the anomalies in, again, a third way, very similar to what we usually see. So what we usually see for the QFT is that anomalies are encoded in triangle diagrams. And this is exactly what we see, that in this case, the anomalies are encoded in these ternary lambda brackets, which we can think of as, well, originating from Feynman diagrams with tree currents. So that's, well, kind of a way to understand why you need these higher products. So in 2D, the anomaly is encoded in just a binary, a biangle diagram, where here it's the triangle. So you need these higher things to make sense of the anomalies. Let me finish the discussion of symmetries and anomalies with this final slide on A maximization. So if you've studied n=1 theories, there's a famous fact that the semi-chiral stress tensor can mix with abelian currents. So in a holomorphic language, this kind of looks like spectral flow. So what in a 2D CFT would be spectral flow here can actually be just thought of as mixing a stress tensor with abelian currents. What we know from QFT is that in a holomorphic QFT arising from some 4D n=1, that flows to a superconformal field theory. There's a choice of superconformal stress tensor that is selected by A maximization, so by maximizing the central charge in this SSS tree bracket. So this can again be thought of as, so you can derive the same thing in the holomorphic theory, where superconformal symmetry now imposes constraint on this ternary bracket, and it tells us that there's, instead of two independent tensor structures, there's only one that can appear, which gives us a well-known relation that people already know from a maximization in the physical theory. But this we can reproduce. But this only tells us a extremization. So one thing that we need to have a maximization is, why is it the maximum and not the minimum? And this is what you can argue for this by unitarity. But that's well, an important thing that is missing in these theories. So in these holomorphic theories, when you do the twist, the concept of unitarity kind of gets lost. So we don't have this nice understanding of unitarity anymore. In the 2D VOs, it's even more extreme. Like the VOAs that arise from 4D n equal 2 are manifestly non-unitary. But there is some hidden twisted unitarity that was recently discovered in this 2D VOA, 4D n equal 2 2D VOA story. So maybe this is a question for future research. What is the role of unitarity in these holomorphically twisted theories? Good. So I've been a bit slow, but let me quickly go through the most important points of what happens with extended supersymmetry. So if we have more supersymmetry, so with n equal 1, we saw that we have some Virasoro, higher Virasoro with A and C central charge. If we have a theory with more supersymmetry, let's just look at CFTs for now. If we have an n equal to SCFT, the stress tensor multiplet decomposes as follows, where we get the usual stress tensor. But in addition, we also get some remaining R symmetry in the twisted theory and some extra operators coming from the remaining supersymmetry currents. And just like in the usual Virasoro, where we can think of this as holomorphic vector fields on C2, all these, if we generalize, there's still some nice complex geometric representation of these things, but I will not talk about this. Let me move on. So we see that in the twisted theory, when you have higher symmetry, higher supersymmetry, there's more structure that appears as this kind of algebra among these, among the stress tensor, the remaining R symmetry, the remaining supersymmetry currents. There's some nice algebraic structure that is left behind after twisting. Still, the space of central charges of this bigger n equal 1 kind of twisted theory is still two-dimensional, so you still just have A and C as we want. For n equal 4 and n equal 3, we actually see that the cohomology shrinks so that we only have one central charge, A, and that is again what is expected from what people know already for n equal 3 and n equal 4 SCFTs. Good. So one final comment, maybe. One final thing to say is that when our theory has extended superconformal symmetry, if we have n equal 1, there's basically only one twist one can do. Every supercharge is equivalent, and you can twist with anything. You get just a holomorphic theory. If you have more supersymmetry, there's many more inequivalent twists. So you can have a topological twist. You can have a topological holomorphic twist. You can have the holomorphic twist. There's many more choices. And you can have these holomorphic, you can have these superconformal twists that give rise to the VOA. So once we do the twist of our holomorphic field theory, we do the holomorphic twist of our theory with higher supersymmetry, we can still access these kind of more refined or more special twists by performing further twists on the holomorphic twist. As an example, we can, for example, deform the differential that we had at the start by this kind of operator that lives in the holomorphic twist. This replaces the Bode differential by this kind of thing. And what we get then is that a further twist by this operator now gives rise exactly to the VOA in the Z1 plane. So so we can compute VOA OPEs starting from our holomorphic twist framework. So it still captures all the information that is captured in this VOA twist, and you can efficiently recover it, at least in perturbation theory. So one thing that is nice about the twist is that, well, as I've already said, it captures all the operators of the holomorphic of the index, but it gives extra structure to this. So the index is just the collection of numbers, but here we have this operator algebra that is put on top of this collection of numbers. So it upgrades the index from just a numerical invariant to some cohomologically graded operator algebra. And this gives us access to much more refined data, and also equips us with an extra set of checks and tools to check or test for supersymmetry or symmetry enhancement. So, for example, we can look at n=1 Lagrangian constructions for Argyres-Douglas theory. What people usually do is just look at the index and see that there is a certain number where if you see there is an additional supercharge. But here we can say more, and we can really see that this additional supersymmetry structure is realized. So there's an additional, you really see an algebraic structure in this twisted theory that tells you that there's that there is more supersymmetry or more symmetry. So it gives you much more. It really organizes everything nicely in multiplets of n=2, and you get a much more refined test to check for supersymmetry enhancement.
I have a question on this. So usually these enhancements, the n=1 theories, they are kind of arbitrary, or they look a bit random from the point of view of the n=2 or more theory that you get at the end. So with your new structure, can you understand why these particular theories, or can you even like predict, given an Argyres-Douglas or higher supersymmetric theory, can you predict which n=1 Lagrangian will, or can you put constraints using your new algebraic object?
I haven't really thought about it in this way. I'm not sure if you can start from an n=2 theory and see if,
or maybe identify a substructure or whatever that would,
So if you give me an n=1 theory, and you do things to it, like giving masses to some, like in the usual Marie-Chisson construction, then it's easy to check, using the holomorphic twist, if this structure is present or not. But going the other way around, I don't really have anything useful to say at this point.
Okay. Yes.
Good. So I've already gone over time, so let me summarize. So in this talk, I introduced the holomorphic twist and a bit of the mathematical structures that underlies it. And I demonstrated that the symmetry algebra, the symmetry of the original n=1 theory is enhanced to an infinite dimensional symmetry algebra. Then the anomalies, they can be efficiently extracted from 3 brackets of conserved currents. And there's a bunch of additional structure in the holomorphic twist when you have extended supersymmetry that gives you an algebraic handle on these additional on supersymmetry enhancement. In addition, we showed how to how you can reach further twists by how you can reach more interesting twists or more exotic twists starting from the holomorphic twist. And as a particular case, you can completely recover the VOA from holomorphic twist by performing an additional twist. There's many future questions. future goals, but since I've already gone over time, let me stop here and leave you with this slide.
All right, let's thank Peter. Very nice. Do we have questions?
Maybe I can ask, it's a very vague question, and maybe I didn't maybe follow all the aspects of the talks, but at the end you said that you replaced the superconformal index by an algebraic structure. And
Yes.
concretely, do you have a good handle on that? That's really, you can compute with that, or yeah.
Yes, that's exactly what we can do. So you can take the index
Mhm.
and every number that you see, if there's a 1, then there's one
There's a one-dimensional
operator.
vector space.
There's like one Q cohomology, one operator in this holomorphic twist.
Mhm.
So then you can really ask questions like, if I have all these cohomology classes, all these protected operators that contribute to the index, what is the algebra among these objects? So if I have flavor symmetry and I have currents, then in the index you just see that things organize into multiplets, and you have to like do a bit of work with these numbers to see this. But here you can really see like acting on operators that are charged with these operators from the currents. You see the action by the symmetry group. So you kind of don't have to do this magic and reorganize everything into characters, but you can really build the multiplet by acting on something with a current. So it gives you kind of a way to systematically,
I see. So it's even computationally, it could even help to compute. Like it could be with more structure, you might be able to compute.
So yeah, if you like suspect that there is a symmetry, but you haven't done this rewriting in terms of in terms of symmetry multiplets of your flavor symmetry, that is like just emerging, you could like just take the currents and act on the fields and see how they act and see if this current algebra organizes into some, in this Kac-Moody algebra for the symmetry you want.
Okay, cool.
Do we have any more questions? All right. So then let's thank Peter again. And we can
Thank you
go
very
off
much
the record.
for having me.